Welcome to this exploration into the foundations of quantum reality. Today we are demystifying some of the most misunderstood terms in physics: observation, measurement, and interaction. Our goal is to establish a corrective framework for understanding how reality is stabilized through interaction-induced decoherence. For over 100 years, a specific linguistic shortcut has dominated popular science. In the 1920s, the realization that measurement disturbs a physical system evolved into the observer effect. This led to the misleading myth that reality only exists when it is being looked at. The physical reality is far different. Collapse is triggered by physical interaction, not human observation. Reality exists entirely independently of us. Misunderstandings of the observer effect fall into a wide spectrum. Some physicists, like Sabine Hossenfelder, Sean Carroll, and Neil deGrasse Tyson, use the term as an innocent scientific shorthand for public framing. Others, such as Forrest and Rick Hansen, use it metaphorically to discuss mindfulness. However, thinkers like Bernardo Kastrup and Donald Hoffman move into metaphysical co-optation, arguing that consciousness fundamentally shapes or generates our reality. The observer effect myth survives by conflating two distinct domains: epistemology and ontology. Epistemology refers to our knowledge of reality. In this domain, observation only reveals what has already been determined by physics. Ontology, however, refers to the existence of reality itself. In the ontological domain, interaction-induced decoherence stabilizes reality long before a human ever looks. To restore precision, we must distinguish between classical and quantum meanings for our core terms. Observation is an epistemic act. It is the awareness of a result after a physical interaction has already occurred. Measurement is a formalized observation or a structured interaction designed to define an outcome. Interaction is the true ontological trigger of collapse, involving entanglement with the environment that causes decoherence. We can view the emergence of reality as a three-step hierarchy. First is interaction, the ontological trigger where entanglement causes collapse. Second is measurement, where we use structured interactions to extract specific physical properties. Finally, there is observation, which is a passive awareness that is strictly epistemic and entirely downstream of the underlying physics. Consider the difference between a hidden dye and an electron. In classical physics, we assume hidden definites. A dye has a specific state even when hidden, and opening the box merely reveals it. Quantum physics reveals observable indeterminacy. An electron exists in a state of superposition until a direct interaction, like touching a wall, forces a collapse. Unlike dice, electrons can share states through the unique mechanism of entanglement. It is vital to remember that collapse is driven by the environment, not by the eye. The process moves from unobserved superposition to physical collisions and environmental interactions. These collisions serve as the ontological trigger for interaction-induced decoherence. Any human observation that follows is merely downstream epistemology. The famous cat paradox dramatizes the tension between quantum indeterminacy and classical definiteness. While the metaphor suggests the cat is both dead and alive until we look, the physics are clear. Countless internal interactions, from photons scattering to air molecules colliding, force decoherence long before the box is opened. Our later observation is purely epistemic. Does the moon exist without us? The answer is a definitive yes. Macroscopic objects are continuously classicalized by uncountable interactions. Sunlight photons are constantly scattering off the moon's surface, and internal atomic collisions stabilize its state. Interaction-induced decoherence does the magic of stabilizing the moon, not our observation. Confusion often arises because we use the word wave for very different things. A light wave is a physical, measurable oscillation of electric and magnetic fields. In contrast, a wavefunction is an abstract mathematical probability amplitude that evolves via the Schrödinger equation. Finally, the probability distribution connects this math to our experimental results. The operation of the absolute square converts abstract amplitudes into real-world probabilities. Electrons do not ripple through space like water. They propagate as probability packets defined by this math. They remain in this state until a physical interaction pins them down. we can finally demystify wave-particle duality. A photon is a quantized electromagnetic wave. The particle property we observe is actually an emergent feature of quantized interactions with matter. It is the quantization of energy exchange, not the act of collapse, that makes photons appear particle-like. In summary, reality does not wait for our eyes to exist. Light is a wave, and particles are emergent features of interaction. Wave functions are mathematical tools, not physical ripples. Most importantly, interaction is the ontological trigger that stabilizes our world through decoherence. Observation is simply the epistemic act of witnessing a reality that is already there.